Hello students, welcome to the world of chemistry. This is Dr. Vikram Panchal, and in chemistry I am dealing with thermodynamics. And in this lecture series, this is lecture number 24. And in this lecture I will explain you about heat capacity in different conditions. Okay. So first of all, you know what is heat capacity now. Heat capacity C is equal to heat absorbed by certain amount of substance to raise the temperature from T1 to T2. So the formula is C is equal to Q upon M into T2 minus T1. And if M is equal to 1 mole, then we call it molar heat capacity. Molar heat capacity, which will be C Q upon delta T. Okay, where M is equal to 1. So this is what molar heat capacity is. Now, as the heat capacity C varies with temperature, it becomes essential to define more accurately in the differential form. So C is equal to dq by dt, and unit may be joule per calorie per mole or calorie per Kelvin per mole, where delta or D represents the inexactness of heat quantity. Inexactness of the heat quantity. And therefore, we need more conditions. So therefore, we have to impose certain conditions. So let us take the first condition, that is heat capacity at constant pressure. It is also known as Cp. So when any chemical reaction takes place, and if it is exothermic, then temperature increases, pressure also increases. Why? Because volume is constant. So when volume is constant, let us see what happens. Heat capacity relates the amount of heat added to the system to change temperature. Remember, to change temperature. Okay, because work is not done as volume is constant. So according to first law of thermodynamics, dq is equal to dE plus PdV. But if volume is constant, then dV is equal to 0. Therefore, dq is equal to dE. Divide both the sides by dt. So dq upon dt is equal to dE upon dt. Okay. Therefore, and dq upon dt is equal to C. Okay. So because dq upon dt is equal to C and it is at constant volume, so we write Cv. So Cv is equal to dE upon dt at constant volume. Okay. So this is the equation of Ce. Once again we can derive this equation another way. Suppose we take E or U, which is internal energy, is a function of temperature and volume. So internal energy is a function of temperature and volume, because if you change temperature, there will be change in internal energy. If you change volume, there will be change in internal energy. So we write dE or du is equal to du by dt into dt at constant volume plus du upon dV into dV at constant temperature. But if dV is equal to 0 because volume is constant, then du upon dV into dV at constant temperature will be 0. Therefore, du is equal to du upon dV dt into dt at constant volume, and that we write d cut qv. So d cut qv is equal to du upon dt into dt at constant volume, and therefore we can write dqv is equal to cv dt. So this is also one of the equation of heat capacity at constant volume. Okay. So thus we can say that the heat capacity at constant volume is defined as the rate of change of internal energy with temperature at constant volume. Okay, so this is all about heat capacity at constant volume. Now second part is heat capacity or molar heat capacity at constant pressure. We call it Cp. So a gas is filled in this cylinder, and if it is heated, P external is constant. At constant pressure means pressure is constant. So expansion of gas takes place at constant pressure, and therefore volume increases, temperature also increases, and pressure is constant. So this is the condition. So according to first law of thermodynamics, we write dq is equal to dE plus pdV. This is equation number 1. Now divide this equation by dt. So we have dq upon dt is equal to dE upon dt plus pdV upon dt. This is equation 2. Now we know that H is equal to E plus PV. This is equation 3. If you differentiate this equation with respect to T at constant pressure, we will get dH by dt at constant pressure is equal to dE by dt at constant pressure plus P dV upon dt at constant pressure. This is equation 4. Now we compare equation 2 and equation 4. If we compare these two equations, we will come to know that dq upon dt is equal to dH upon dt at constant pressure. These two will be same. Okay, and therefore we write dq upon dt is equal to dH upon dt, and dq upon dt is also C, but at constant pressure, so we write P also. So we write Cp is equal to dH upon dt at constant pressure. Okay, so this is the formula for Cp. So thus heat capacity at constant pressure is defined as the rate of change of enthalpy with temperature at constant pressure. Okay, so that's it in this lecture. Thank you so much.